when the output reaches from its rise. So we'll calculate from the rising point. Okay, so this is for just one step input, right? So as we saw, there are I think 4, 5, 6, 7, 8. I think 4 step response data. So you will, for each of them, you will plot, you will calculate the gain and time constant and time delay for each of them, and then you will obtain the parameters as an average of all of them. Okay, is that clear?
Abhinav, just one question.
Yeah.
Similar to this step response which we are doing for 5 to 6, whatever amount of data that we have, like that we will have to plot it for frequency as well for all the frequencies.
For the frequency, I have already plotted the step. I mean the stem plot, right?
Yeah, so this stem plot, I'm asking whether we'll have to show it in the report for all the frequencies.
Stem plot, no need. You need not show for everything, but step response plot, since there are only 4, I think you can show that.
Yeah, yeah, noted.
For the, you need not put the stem plots. Maybe you can put the gains from them in the report.
Yeah, clear.
Okay, so now once we have the step response, we now we have finalized our parameter, the values of the parameters in our transfer function. So are there any doubts till now?
Come again, sir. Please ask the question again, please.
Yeah, I'm so here now we have completely found out what the values of individual parameters, right? So I'm just asking if there are any doubts till this point. No doubts. Shall I proceed?
I think once we do something that some doubt may crop up, but we'll proceed further.
Yeah. So you understood how we measure each of those values from the step response, right? The gain and all. So you can do it repeat the same for all the various magnitudes of gains, and then various magnitudes of the inputs, and take the average of all of them. So now once we have the transfer function, what we now want to do is we want to design a PI controller, right? So what is the function of a controller? Why do we design controllers in the first place?
We want a desired input, like basically to when we have a system, we want to behave it like for a given input, it should be predictable. How do we control in that way? So
Okay.
just to add a predictive behavior, or I would say a fixed behavior of the system, we require controller. Otherwise,
So
get
yeah.
wild.
Yeah. So in general, we design controllers for getting the desired performance. So in this case, so we are dealing with the braking system, right? So when the driver gives the brake input, we want it to respond it in a certain time. We don't want, like, what are some of the basic expectations from our braking system? We don't want it to delay too much. We want it to respond within certain time limit, and then what we may want to limit how much away it goes from the required input. Maybe the driver has pressed just till half braking input he is giving. He is not pressing the pedal completely. So we want the brake system to give the half of its capacity. So we may want to next thing is we may want to settle at a value. We don't want it to fluctuate too much for too long time, so on, right? So these are some of the practical considerations when we are dealing with the braking system. Now, so for our problem, the constraints given are these. So we want that the maximum peak overshoot should be less than 10%, and the settling time should be less than 0.8 seconds. So now we'll discuss how we'll design a controller using our RL tool, right? So I'll consider an example transfer function and show you, because you will have to calculate the transfer function specifically for this braking system later. So when you get the values, you follow the exact same procedure. So I'll take an example transfer function and show you, right? Yeah. So this is the transfer function I chose. So how you define? Sorry, I'll start from the beginning. So how you define a transfer function is, first of all, you will define the system. Let us say my planned transfer function is, let us say my planned transfer function is, s plus 1 by s plus 2. So what I'll do is, my sys will be tf is a function I use to in MATLAB for defining transfer functions. Then we'll pass uh, arrays, arrays as arrays with the coefficients of the numerator and denominator. So my first array will be the numerator coefficients, starting from the highest degree of s to the lowest degree. So let us say if my transfer function is s square plus s plus 1. So what my input will be, s square's coefficient is 1, and then s its coefficient is 1, and then 1, right? So this will be my numerator. Similarly, my denominator, let us say my denominator will be s cube, 2s cube plus 3s plus 1, right? So then 2s cube. Then what? Do I have an s square term? No. So I'll put 0 for the s square term. Then s plus 1. So this is how I define my transfer function. So if you press enter, you'll see that the transfer, it shows me how the transfer function is modeled, that is s square plus s plus 1 by 2s cube plus s plus 1. Is this clear how we define a transfer function? TF is the function we use.
It's clear, sir. But
Yeah,
again,
okay.
we will do it
Huh.
and then come back to you once.
Yeah, yeah. Or these things I think you can follow right now. Maybe you can you define the transfer function given here right now?
It is there, no, sir. You have written the plant term function like this
Yes,
is.
yes, yes. Yeah, just
Yeah.
you can do along with me so that it will be more clear. And if you have any doubts or errors or anything, you can directly ask me right now.
So the problem is that we are having a single screen. So if we do this, then probably we'll lose your screen actually.
Oh, okay, okay. Everybody is okay. Yeah, if someone, I encourage, if someone is, it is possible for you, you can try it out along with me so that if you have any doubts then and there that pops up, you can directly ask. So now, if I want to, the tool that we use, the built-in tool in MATLAB that we use in uh, to design controllers is RL tool. So we essentially plot the root locus and then see how where should I keep my poles such that my desired performance is achieved. So RL tool of my name of the transform, that is sys, will give me the window. The RL tool window will open, look something like this. So the transfer function I have used is this one. Yeah, you can see the transfer function, right? This is the transfer function I have used. Now, right. So Just a second. So you're able to see this window, right? This is the root locus plot, and this is our the step response plot. So the layout I'll explain you briefly. So here on the left you have the blocks transfer function of each block involved in our model. So if you see, if you click on the architecture, edit architecture, you see a diagram above. So you can see what is the name of each block corresponds to which part of the model. So you can see my C is a controller, G is my plant, H is my feedback transfer function, and so on, right? So here G is my plant. So if I want to see my plant transfer function, I'll go here. So the value that is the transfer function is this. This is what I have plotted. So now this is the root locus plot, and you can see two squares, right? So for the pole positions where when they are here, this is the step response. So this is the step response of this pole position, and I can drag and see how my step response varies as I change my k. So as the poles move with k, so I can see how my step response varies, right? So this is the utility of RL tool. So now in RL tool, I have this provision for uh, finding out what are the regions for my required performance requirements. So what I'll do is, so I'll right click on this plot. This window will open. Here I'll go to design requirements, right? Design requirements, and I'll select new. So here this window will open, which will enable us to select what are the design requirement constraints that we have. So if you recall, we have two constraints. That is, one is our percentage overshoot should be less than 10%, and the settling time, which should be less than 0.8 seconds, right? So we'll input those two constraints. So first is my settling time should be less than 0.8 seconds, and you'll see that a region of the my root locus plot will turn into this cream color. So what this means is, for my uh, given constraints, the white region is the only feasible region. If my poles go into this cream colored region, I'll violate my constraints. So that is what the function of this define and design requirements, and how it reflects on the plot. Now my poles are here, right? So now my poles are in white region, so I'm fine. My 0.8 second requirement is met, and also I have one more constraint as well. So that constraint is on the peak overshoot, right? So I'll put that as well. Yeah, you see now some other regions have been added into the constraint zones. So we cannot end the poles when they are in the white region. Our constraints will be met. So you can see that the poles I can without even the controller, I can make the forced to stay in the white region. But for this experiment, we are learning how we design the PI controller. So for that, what we'll do is once we have once we have implemented all our constraints, now we go for our PI controller design. So if you see our PI controller design, just a second, I'll input my stylus. I'll connect my stylus device so that I can write.
While
Abhinav, just
Yeah.
to,
how did you actually go to that control system designer after plotting the transfer function?
Yeah, I have input the command RL tool, and the name of the
Yeah,
transfer
sorry,
function.
didn't follow that. Yeah.
Yeah.
Just one doubt here. Like, how does the system, like, you have defined the variable sys, and like you're calling RL tool of plant. So how both of them are getting linked?
No. This system I have shown just for an example.
Okay.
I have defined another system. I mean, another
Oh,
transfer
okay,
function here.
okay,
That is
okay,
what
okay.
I'm plotting.
Understood. Right, right.
Oh, sorry for the confusion. This I have shown just for telling you how we input, how we tell it to create a transfer function.
Mm-hmm. Clear. Yeah.
sir, while doing this project, suppose if we are getting stuck somewhere,
Huh.
we can write to you, or we can reach to you, sir, or a mail, and
Over mail, whenever you get it, you get any, you're stuck up anywhere, you can always reach out to me. You can
and
always.
one more request, sir. What is the timeline for submitting this project, sir?
I'll announce it at the end of the session. Okay, we have discussed it in the beginning with someone else. I'll
Oh,
announce it at the end of the
I'm
session.
sorry, sir. Okay, sorry. I just missed it. Not a problem.
Okay. Right. So is my screen visible? I am sharing a OneNote window. Is that visible?
Yes, visible, sir. Visible.
Yeah. In general, when I have a plant with a transfer function, so yeah, if this is my plant and this is my controller block, so if I have a PI controller, what will be the the form of the transfer function, how it will affect is, if I have a PI block here and this is my plant. So if my plant, I say here is G of S. If my plant is G of S, when I have a PI block, if I only have a proportional controller, it will be Kp times G of S, right? That will be my transfer function of the controller plus transfer. I mean the plant, when I add a just a proportional controller, right? And if I have a PI controller, what it will be? Kp plus Ki by S times G of S, right? Is it true?
Yeah.
Yeah. So this will be my combined transfer function once I have the PI controller. So now what I designing a controller means what? So I want to essentially find Ki and Kp. right? So now when we have this kp and ki, so essentially what we are doing to our transfer function is, if I simplify this, it will be kp times s plus ki into g of s. Sorry if my handwriting is very poor. So this will be my final transformation, right? So now what happened when we have input PI controller? We have added a pole and we have added a 0, right, to our original plant transfer function. Is this understood?
Yes, a clear, sir. No problem. It's fine.
Yeah. So now we'll convert this change into our original MATLAB, our root locus plot. So, so, so first I have implemented my constraints and they have reduced my feasible region. Now to input an integrator, what I'll do, I'll go to this.
Abhinav, how did you introduce that constraint? Sorry, can you repeat that?
Yeah, sure. So if when your plot is like this, initially your plot will appear like this, right? So now,
Yeah, we have the same plot. Yeah.
So right click on the plot,
Okay,
and
okay.
this pop-up window will appear. Then go to design requirements.
Okay, got it. Yeah.
And then new. So for each new design requirements, you will create one new design requirement and input your constraints.
Understood. In our case, we are going for settling time 0.8 second and 10% overshoot, right?
Yes.
Okay.
So this shaded area is feasible zone, right now, Abhinavji?
Which one, sir?
This shaded area, what is being shown in what I'm going
No,
to say
this
yellow.
shaded area is infeasible region.
Acha, okay, okay.
Our
Only
pole should not
white
go to
area
this.
is okay.
White
Right,
area
right.
is my feasible region. I should
Yeah, I got
stay
it.
within the white region. Yeah.
Yeah, fine. Thank you. Sorry. I just.
No problem. So now I'll put my PI controller. First, what I'll do, I'll put an integrator. You can same right click. The first option, add pole or a 0. You can see you have various options. You can add a real pole, complex pole, and so on. And here you can see an integrator. When you put an integrator, what happens is essentially a pole gets added at 0 at the origin. A pole gets added, right? So that's what an integrator will do, because integrator is just this term, right? So that's what will happen. And then then what we have is we'll have to add one more 0, because we have this kps plus ki term, right? So this will correspond to one real 0. So I'll add a real 0 here. Add a polar 0, and you can see a real 0 option. Click on that, and then your mouse will turn like this with a small circle at the on the top. So this means you have to choose where you want to add your 0. So I'll put it here, right? So now I'll go to according to my architecture, what is C is my controller block, right? C is my controller block. So currently my controller block transfer function is this one. This is what this shows. That is the value of kp times s plus ki by kp by s. See, because this is my transfer function part, and this is my controller. This is my controller part, right? So in my controller part, if I take kp out, I'll be left out like this, right? This is the form I'll get. So you can see the same thing here. You can see it here, right? block which I'm tuning is my controller block, and its transfer function is this. Understood? So now in this I want to essentially bring my poles into the white region, right? So for that, what I'll do, I'll click, I again right click and click on edit compensator. Yeah, a window will appear like this. So here, whatever integrator real poles zeros you have added, those you will be able to tune it here, the compensator essentially. So here my real pole location is at minus 14. So you see the poles are very close to the origin, right? So, and I want to bring them this side. So to compensate for the real zero added real pole added at the origin, I'll bring my real zero very close to origin. Maybe I'll bring it to around around -1. It seems to appear good, right? So now I have my poles in the white region. So I'll see I'll go to my limit, because essentially when my poles are crossing this line, I'm violating my which constraint? My maximum peak overshoot constraint. So the best optimal solution will be just on the border, right? Because I want my what the system to react very fast, and at the same time I don't want it to go overshoot too much. So I'll see what I can do so that my poles can be placed, uh, in the border of the white region. So if I do something like this, so yeah, my step response looks something like this, and I can actually measure the response characteristic. You can right click on the step response characteristic. We have a we have what is the constraint on settling time, right? So I'll just to measure that, I'll put this constraint, and then peak overshoot as well. So before I go there, I'll change my, you can see my settling time is still very high, right? Uh, yeah, settling time is 2.32 seconds. So I'll bring it very closer, maybe to 0.2. Oh, it's becoming unstable. Then I'll change this to no, I need high gain. So essentially what we are doing is we want to place the poles such that my constraints are met. So for that we are finding the value of suitable Kp and Ki values. So I want to there is one pole here.
Abhinav,
Yeah.
there is no voice. Yeah, yeah. You okay? Okay, you are aligning that as well. I
Yeah.
thought that.
No.
Suspect.
I'm trying to bring the system to our design
Right.
requirement. Yeah.
Sorry, we thought we lost the connection. Okay.
So now you can see that yeah. So you can see that my my response settling time has come below 0.8 seconds, 0.792,
Yeah.
and my overshoot is 1.21%. So my PI design is done, right? So this is how we design our PI controllers, right? So generally, for when we begin, I have directly put both integrator and proportional. So one way to simplify this is first put just the P. So I'll if you put just the P, uh, what will happen is uh, you will be able to drag the poles directly and see what the just putting a proportional controller can do, and then put the you know uh, integrator to see how it changes, because when we want to vary two variables, no, we we may get lost as to how we may not know where to start or where to end. So general procedure suggestible is you start with just putting a P. So I'll show you how. So design requirement, sorry. So I have my link end of 0.8 and my peak overshoot 10%. Now, if you click on C, yeah, my gain value is 1. That is, I have just the poles at their original position, and with gains k equals to 1. So as I see this, as I move the poles, you can see that my value is increasing, right? This value is essentially kp. Why it is kp? Because in our transfer function, if there is no integrator and all, so any gain, if I have if I have the root locus plot of g of s with the plan transfer function g of s, and then root locus plot itself, the definition of root locus plot is when k, the variation of k, right? As the k increases, you are seeing how the poles will vary. So here the k in the uh, root locus plot implies that there is a kp whose value is 1 earlier, and now you are increasing the kp value. That is essentially putting a proportional controller. So as you increase the kp value, so you can drag and see that for this value what are the response characteristics, right? So peak response and uh, settling time. So then you'll get an idea of where to put the pole and zero when you put the PI controller. Okay, is this clear? Any doubts on how we design controllers?
So we will try, sir. We will try and then.
Yeah, you'll surely. I hope that you'll get doubts, and you can always write a mail, or if it is essential, we can always have one-to-one sessions also. I'll be available to clear your doubts.
Sure.
So coming to our deadline, yeah. So we were discussing that 4th of April will be a good time. I think someone agreed for 4th of April. Is it fine for everybody?
Yes, yes.
Yes, sir. Yes, sir. We will try.
Sure.
If something comes 1 or 2 days, kindly complete.
Yeah. Okay. Yeah, we can consider that in emergency situations.
Abhinav
No
sir, only
problem.
background was because this week we have project review and then by
Yeah,
this
I
week,
understand. I understand completely.
that's the reason.
Sure. One day, 1 or 2 days, we'll see if it becomes too much hectic, or an emergency case, we can surely postpone 1 or 2 days. That's not an issue.
Thank you. Thank you.
Yeah, because someone brought out the point. It is a yeah that but the next project I'll start discussing on the 7th, on the Monday 7th of April. So by that time, if you are able to complete it and submit, then you can concentrate on the second project without any
So
disturbance.
next Tuesday will not be there, sir.
Uh, Next Tuesday, sir told, I think I won't be taking next week's.
Okay. Understood.
Next Tuesday and Wednesday, I won't be
Right.
taking.
Okay, understood. Thank you.
Yeah, thank you. If there are any doubts, you can ask, or else thank you for attending.
Yeah. 1 minute, sir. 1 minute, sir.
Yeah.
Am I audible?
Yes.
So I just want to chronologically tell the steps that we are going to be following, just in case, because when we attempt MATLAB so that it goes properly.
Yes.
So first thing will be we'll actually load the data of frequency response data.mat file. Then we will get the workspace for the frequency. Second, we will try to load the step response data.mat file. We'll get the workspace variables for the step response as well. And then we will plot the frequency plot for each frequency varied by 0.1, the next frequencies, right? All those frequencies we'll plot until 1.2, right? So we'll plot all the frequencies.
Yes.
And then we will get the semi-log x plot of this, which is nothing but my how do I tell that stem function plot? Yeah, the stem plots, right?
Yeah, my spectrum function that is given, that will give you the stem plots. So from the stem plots, you will have to extract the gains, and from the gains you calculate 20 log output by input, and then you have to plot the Bode plots.
So basically, after getting the workspace variables of the frequency as well as step, the first thing that I'll be running is plotting of each and every frequencies using the plot command, and then I'll have to use my spectrum. Am I right?
Yes. Plotting for each of the frequencies is just for visualization.
Yeah, it's visualization. Understood. That's clear. Maybe to add to the report, one of the graphs we can use that.
Yeah, sure.
So that my spectrum will take two inputs as variable. Two arguments for the function to be running, right?
Yes.
So those arguments are essentially
My input and output.
yeah, the input and output, which is my voltage and my pressure.
Yes.
Okay, understood. So correspondingly,
The
whichever
entire
is the
column of
corresponding column of
input
the
and output.
this thing. Okay.
Yeah.
Individually, I'll have to give it for each frequency, right? My spectrum.
Yes. Individually, you'll have to do.
Okay, so essentially, if I'm having 11 or how many ever is my frequencies, those many times I would have run my spectrum plot.
Yes.
Spectrum function, sorry.
Yeah.
So after that, I'll be doing my step response plot also, which is similar to what you just showed us today. Yeah. So if I'm right, that command goes like this. Just a minute. So it will be figure. I'll be using a figure, and then I'll plot the step response for 5, 6, and 7, 8 like that for 1, 2, and as well as 1, 3.
Yes.
Which is my time versus voltage and time versus pressure as well. Correct?
Yes.
So once I plot my step function, then I'll go to getting my getting the slope from it.
No
Like get
slope.
the
Yeah, the parameters, not the slope. The parameters we have discussed, right? The gain,
sorry, yeah, I mean
time
the
constant, and so on.
parameters that we're talking about.
Hmm.
So meaning the to get the transfer functions parameters, those
Yes,
parameters.
yes,
So then I
yes.
put my transfer function using the SF command, right? Or correct command is
Yeah, TF,
TF, sorry,
transfer
TF,
function, TF.
yeah, TF command. TF command will have a numerator as well as denominator as the arguments in that function,
Yes.
and the plant
The
transfer function will
arguments
get
will be the coefficients as an array.
coefficient as an array, correct? Yeah.
No, no,
Sorry.
no, I'm sorry. I'm Prem. Please continue. I'm sorry.
Yeah, please be on mute. Yeah. So once we get that plant transfer function, we'll use the R locus tool to plant that to give plant as an input to that, and we'll
Not
go
R
into
locus.
the
R locus will just give you the plot of the root locus. RL tool is the function.
yeah, sorry, RL tool we will use, and the input will be the whichever variable I declare as my plant,
Yes.
and that will take me to my controller designer window, wherein
Yeah.
I'll have to initially the plot will be without my constraints. I'll have to introduce constraints one by one.
Hmm.
So initial constraint will be settling time and my which is what was the other
Peak overshoot.
constraint? Settling time
Peak
as well
overshoot.
as peak overshoot.
Peak overshoot.
Yeah, once I give those two, my regions will get constrained. After that, I'll introduce a p value and then I'll introduce a integrated value, correct? That's how I'll
Yes.
go about.
Yeah.
When I introduce my p value, c value will currently be at 1, and if I vary the pole and see whether it is closer to my feasible region, so according to that, whatever p value I have to decide.
Yes. That is when you decide proportional
Only
control.
for p, if I'm using, then that will be the case. But if I use integrator also, probably the coefficient value will change.
If you when you use the integrator, because you'll have to, there'll be a pole and zero included, so
Yeah, got it.
you will include the integrator and then a zero, real zero.
Okay, and then we'll one by one vary to get the correct, correct step response plot also for
Yes.
that area.
Yes.
So this is the end of this thing. Okay,
That's
understood. Yeah, thanks a lot.
And-
But final result will be it will be subjective. Like let's say each one of us will receive multiple options, but whatever satisfies all the constraints is sufficient.
Yes, it should satisfy the constraints. Yeah, final answer will may vary. The exact position of the poles will may vary a
Yeah,
little bit.
exact questions of the poles might not be on the same coordinates. That's what Rahul is trying to say. Yeah.
Yeah, that's true.
And sir, one more request. Basically, like if you could say some the format of the report that you are expecting from us.
Yeah, report. I think what all to include. There is a. I have shared the, the file. No, I'll show you once more. No problem.
Okay.
Yeah, you have given a Word document where that is there, right? I mean, modeling the plant part A, part B, controller design. Those steps only, right?
Yes. So your report, here the project report should include this. Part A will be uh, plot the step response and mode and magnitude plot, include the explanation. So you'll everywhere when you decide that this is first order, every time you write a conclusion, you will have to write the reason for your conclusions. And okay, then how the transfer function parameters are obtained. Then part B is the with the Paris approximation, you'll design the transfer function, and then how the parameters were obtained. Okay, and then part B is essentially the controller design.
Abhinav, just one thing. Sorry to interrupt.
Yeah.
After we plot that my spectrum for each and every one of those inputs, we have to use that mag dB equal to 20 into log 10 and then get the mag and then go for semi-log exploit, right? That's how we get the Boolean.
Yes, that's how you get the Boolean.
I missed that step. Yeah, sorry. Yeah, got it.
So output peak by input peak, 20 log of that will give you the gain.
Yeah.
And then semi-log x of that with the frequency. So then the results will be the the gain, overshoot, settling time, and steady state error of with the graphs. That's all. That will comprise your report.
Okay.
Thank you, Aminu.
Thank you.
Yeah,
Thank you very
thank you.
much. We'll meet on 7th.
Yeah, sure. Thank you.
Thank
Thank
you.
you.